Hello. How are you all doing? In this video, I am going to solve in detail each of the math exercises from the 2026 Guide for Admission to UNAM. Specifically, I am going to solve these, which are from Area 4, that is, from the Humanities and Arts area. So come on, let's get started. The first math exercise that appears in this guide is number 41, and it says, what is the result of dividing 1/10 by -1/2? All right, let's write down the operation here. We have 1/10 divided by -1/2, so we can separate it. I'm going to put a parenthesis here, and now let's write -1/2. Close the parenthesis. This is the operation we have to do first. Let's work with the signs. If this number doesn't have a sign, it means it's positive. So we have positive divided by negative. We already know that plus divided by minus equals minus. So we write the minus sign. Now, to solve the division of fractions, we just have to multiply crosswise. That is, I'm going to multiply 1 by 2. 1 times 2 equals 2, and this goes in the numerator. Now let's do the denominator so we can calculate it. We just multiply crosswise again. That is, I multiply 10 by 1. 10 times 1 equals 10d, and this goes in the denominator. Done. Now we just need to simplify the fraction. Here we can calculate half and half, right? Come on, let's copy the minus sign. And now we calculate half of 2, which is equal to 1 over, and we calculate half of 10, which is equal to 5. Done. The result is -1/5. So let's see what that corresponds to. Where is it here, right? So, the answer to exercise number 41 is -1/5. Done. We're finished. Simple, right? All right, come on. Let's move on to exercise number 42. It says, when multiplying the square root of 2 by the square root of 2, you get, well, it's very simple. Also, let me copy the exercise again. Look, if we have the square root of 2 times the square root of 2 here, all we have to do is write it as the square root of 2. But to what? Well, squared, right? Because we have the square root of 2 times. The square root of 2. That's the square root of 2 squared the root, and the square cancel each other out, and I'm just left with 2. That's it. The solution to exercise number 42 is 2. It's that simple. So let's select option B. Done. We're finished. Perfect. Let's move on to exercise number 43. Simplify the following fraction. Here we have the fraction and 4 possible answer choices. I'll work here directly, okay? The first thing I'm going to do is separate. So I'm going to put this term over 2ab, then I'm going to put this term over 2ab, and finally, well, the same, this term over 2ab. You know? So let's see. Let me write it down really quickly. Once we have it separated like this, we're going to do the divisions of monomile by monomile. Here, we have monomiles divided by monomiles, right? So, let's go. We divide 8 by 2, which is 4. Then the a squared divided by a just leaves me with a, right? Then here we have b divided by b, and here we're going to say that b divided by b equals 1. Well, I'm going to say they cancel out. I'll put it in quotes, because they don't really cancel. It's just that the division equals 1. So for that reason, I'm going to remove the b's, and I also have a c left over here. So does that mean the answer should start with 4ac? Let's see if there's one that starts with 4ac. Not this one. Look, this one says 4 before Christ, so not 4ac. This one could be, then the next one says 4 before Christ. So it's not that one either. Then the other one says 4 before Christ. It's not that one either. So, are we done? The correct answer is the one in option B. As you can see, that's the solution. Anyway, I'm going to continue, even though at this point we already know the answer, but I'll keep going, because we're going to see if in fact everything else matches up, and also so you can practice a little more. So, let's continue. I'm going to put the minus sign, and we do 4 divided by 2, which equals 2. Then a cubed divided by a leaves me with a squared. Then we have b to the 4th divided by b. That leaves me with b cubed, And finally, this c squared. Well, I'm just going to move it over. Then it continues over here. We can also cancel some things. For example, the 2 with the 2 cancel out, the a with the a cancels out, and the b with the b cancels out. And what do I have left? Well, just the c. So the solution has to be this one I'm boxing here, which is 4ac minus 2a squared b cubed c squared plus c. If we have that as the answer, right? 4ac minus 2a squared b cubed c squared plus c. If everything is correct, then that's it. We finished the simple exercise, right? All right. Let's go with number 44. The product is given to us here. A multiplication of algebraic fractions is equal to. Well, what we have to do is first multiply and then simplify. Since this is already factored, it's really not convenient for us to do that. So here, in this word, this product, well, in what it says about the product, there's a bit of trickery. It's really because we don't actually have to carry out the product as it is. We don't have to solve the multiplication. Okay, you just need to see if something can already be canceled. And look, I can quickly see here that this x minus 1 can be cancelled with the x minus 1. Remember that when I say cancel, in this case I mean that the division equals 1. That's why I can remove them, and I'm just going to write what's left. What's left? That's it. Well, in the numerator, x squared minus 3x. And in the denominator, I'm only left with x minus 3. See, this fraction is already simpler, right? But we still haven't reached one of the ones over here. So let's keep going here. I want you to notice that we can factor out a common factor in the numerator. What's the common factor from what I have here? Well, it would be x, right? Or well, from this binomial, what's the common factor? Well, it's x. So let's put x. We open parentheses and say, what do I multiply x by to get x squared? Well, it would be x. Minus, what do I multiply x by to get minus? 3x, well, by minus 3, right? And that's it. This way, notice that if I expand this, I would get back x times x, which is x squared over here, and then x times minus 3, which is minus 3x. So, here I'm already factoring. Now why am I factoring? Well, to see if I can cancel something again. In this case, I want you to notice that this x minus 3 cancels with this x minus 3. And what am I left with? Only, well, just x. Therefore, the answer will be option C, right? And then we circle option C. Done. We're finished. Let's go. With exercise number 45, solve the equation 5 plus x over x plus 2 equals 1. Look here. This might seem complicated because we have a fraction here, and we also have a denominator where the x is. But don't worry. What we're going to do is multiply by this same denominator, but on both sides of the equation. What do I mean by that? Look, let me rewrite my equation again. There, we have it rewritten here. Now what I'm going to do, I insist, is multiply both sides of the equation by x plus 2. So I'm going to do that. We multiply by x plus 2. By doing this, what I'll achieve is that I no longer have a denominator. Right? Come on, let's do it. So we multiply both the left side and the right side by x plus 2. Come on, times 5 is 5x. We write 5x. Then 2 times 5. Well, that's 10. Okay, so I've already multiplied by 5 to this x plus 2 that I just wrote. Or, well, x plus 2 times 5. Now see what's going to happen here. I'm going to have x, which will multiply by x plus 2. But then it's going to be divided by x plus 2, right? So in this case, I could cancel the x plus 2 with the x plus 2 if you're following me on that, right? Remember, I would be multiplying x by x plus 2 and then dividing it by x plus 2. This would make the x plus 2 and the x plus 2 cancel out, and I would only be left with the x, right? So multiplying x plus 2 by x over x plus 2, well, I'm only left with x. And look, I won't have denominators anymore, right? Well, finally, we multiply 1 by x plus 2. And well, 1 times x plus 2 is still x plus 2. See? Now we have a super simple equation, and it's going to get even simpler, because this x cancels out with this x, right? That's because I'm adding x on both sides of the equation. Or you could see it as this x moving over as a subtraction, and with this positive x, they'll cancel out, right? Ready? So on the left side, I'm only left with 5x. On the right side, I still have a 2, and this plus 10, I can move it over as minus 10. So on the left side, I still have 5x. And on the right side, I have 2 minus 10, which equals negative 8. That 5 we're going to divide by it. So we get negative 8 e⁻⁵. There you go. This right here is the solution. X equals 8 to 5, where is that? Option A, right? X equals negative 8. That's perfect, all right? We're done. Let's move on to exercise number 46. The solution to the inequality. We have an equation here, and they give us 4 possible answer choices. It's something I've had a bit of an issue with in this guide, because they usually call it an inequality, and I've mentioned it in previous videos. This right here. Well, even though it is an inequality because it has a greater than sign. But, specifically speaking, when we're going to find the value of x in an expression like this, we're actually talking about an inequation. So, I'm going to correct it here, because this really is an inequation. Okay, it would just be an inequality like this. If I had, for example, 5 greater than 4, that would be an inequality. 5 greater than 4. But when we have, I insist, some variable, well, really? Or an unknown, then we're talking about an inequation. Okay, let's go ahead and solve the inequation. To solve it is pretty simple. We're just going to follow the same rules we use when we solve equations, but with a slight change. You'll see. Watch, I'll do it here. I'm going to leave this 3x on the left side, just as it is now, and I'm going to copy the greater than sign we have here. I'm also going to leave the negative 8 and this plus 4 since it's positive. I'm going to move it as a negative. So on the left side, I still have 3x greater than negative 8 minus 4, which in total is negative 12, right? Now this 3 is multiplying, and if it's multiplying, it goes to the other side dividing. Careful, here I'm going to write the x, but instead of copying this greater than sign, I'm going to put a less than sign. Do you know why? Because there's a little rule that says when you multiply or divide by a negative, you have to flip the inequality. So in this case, since we're dividing by a negative, that's why I'm going to flip the inequality. So here I'll have x less than 12 divided by 3, right? And finally, we do the division. Negative 12 divided by negative 3. So negative divided by negative is positive, and 12 divided by 3 is 4. Let's see. I'm saying that x is less than 4 if I say that x is less than 4, it means that x, for example, could be negative 500, right? Or it could be 0, or it could be 3.9, or it could be 1. 0, 0, 0, 0. So, starting from 0, but to the left, it can take all the values, right? If I wanted to quickly make a graphical representation, I would do it like this. Look, we draw a line and put, for example, 0 somewhere, just as a reference point. And I'll put, for example, let's say 4 here. It's telling me that x is less than 4. So at 4, I'm going to go up and put an open circle. Now, from here, I'm going to go to the left to represent that x is less than 4. Over here on the left side, we would have negative infinity, and on the right side, we would have infinity, right? Therefore, I want you to see that the interval of values for x goes from negative infinity. Okay, without touching it, obviously, it just comes from there. And up to what value does it go? Well, it tries to reach 4 well. It gets to 4, but without touching it. Okay, that's why, since it gets there without touching it, I'm going to use a parenthesis. If we had a less than or equal to here, then I would use a bracket here, okay? If there was a less than or equal to, I repeat, I would use a bracket. But since it's saying that x is less than 4, it means it doesn't touch 4, right? For that reason, I use a parenthesis. So, what we have here would be the solution, given in interval form for this inequality. So, what would the solution be? From negative infinity to 4. Where is that here, right? Option from negative infinity to 4. There it is. All set. So we finished exercise 46 as well. Let's move on to 47. What is the solution to the following system of equations? They give us the system and also some answer choices. Look, let me do it again. Well, I was going to, right? If I'm going to copy it, let me just copy it. I didn't want to copy it because I thought I could work directly with it there. But honestly, if I work directly there, everything will end up really cluttered. So I'd rather rewrite it. Okay, I'm going to use the addition-subtraction method, also known as the reduction or elimination method. This consists of adding or subtracting the equations in such a way that one of the unknowns is eliminated. In this case, for example, what do you think if I multiply the first equation? Well, both the left and right sides of the first equation. By 4, why would I be multiplying the first equation by 4? Because, as you can see, when I multiply 4 by y, I will get 4e and 4e minus 4. And well, that will give me 0. 0 what? Well, 0. And that way, we could solve for x, right? Let's do it. So we multiply the first equation by 4, 4 times 3x gives me a total of 12x. I'll write it here. 12x, then 4 times, and that's equal to 4e. And on the right side, we have 4 times 8, which is equal to 32. I'm not going to modify the other equation. I'm just going to write it as it is, which is 2x minus 4y equals negative 4. And now I want you to see that if I add the two equations, the y's will be eliminated. So, how can I eliminate the y's? And now, can I solve for x? We do 12x plus 2x, and in total, I get 9x. Now let's do the y's. Plus 4y minus 4y, so the y's cancel out. Now let's look at what's not x or y. That is, what's on the right side of the equations. 32 minus 4 is equal to 28. And from here, I have that 14x is equal to 28. Therefore, I can divide by this 14. Right? And when I divide, I'll have 28 divided by 14. And how much is 28 divided by 14? Let's see. Think about it. It's 2, right? Very good. So now we have the value of x equals 2. Once we've found the value of one of the two unknowns, what we can do is simply substitute into either of the two equations. In this case, I think it's much easier to do it in the first equation, right? So come on, let's substitute the value we found in this case, I insist, into the first equation. So I have 3 times whatever x is. We'll put that in a moment. Plus y equals 8. So let's put in the value we found for x, which we saw was 2, right? All right, we do the operations. 3 times 2 equals 6, so I have 6 plus y equals 8. We're going to move this 6 to the other side by subtracting, so I get that y equals 8 minus 6. And from here we have that y equals 2. There you go. We also have the value of y. Easy, right? So, what will the solution be? Well, that x equals 2 and y equals 2. That's the correct answer. So this one wasn't it either. Let's circle the correct answer, and we're done. Let's move on to exercise number 48. Exercise 48 says, find the domain and range of the following function. Y equals negative 5 over negative square root of x plus 2. Look, so that everything we're going to see from now on about domain and range is clear, because these aren't the only exercises. Actually, this isn't the only exercise where they'll discuss domain and range. I'm going to explain to you briefly, even if it's very briefly, what domain is and what range is. Let's see. Imagine that we have a curve, for example, like this one. Let me draw it more or less like this. Let me fix it. I'm going to draw it. Well, I think it's fine here, right? A little more this way, it's just that I want to get to something in a moment. Okay, look, I'm going to put the scale here. For example, sorry. Well, here I'll draw the axes properly. Like this, with the arrows. This is the x-axis and the y-axis. Okay, well, here we put that. This is 1, and over here, we also put that this is 1. Now I have all the information. Look, imagine that we have this curve, and this curve is just that. I mean, it just starts here and ends over here. Okay, and we want to find the domain. Well, the domain is going to be that interval of values that x can actually take. What do I mean by that? Look, for example, if you were standing here and looked down, how can you tell if the curve is there? I mean, if the function exists when x equals 1. Therefore, that means 1 is part of the domain. Now, if you stand here at 2, look down, here's the curve. What does that mean? Well, that 2 is also part of the domain. And at 3, 2, if you stand and look up, here's the curve. And at 4, 2, if you look up, here's the curve. So, does that mean that up to 4, you're going to have values with respect to x? That if they're going to touch the curve, well, that if they're going to hit the curve. Because if you stand, for example, at 5, there's no curve here, neither down nor up. Well, neither up nor down. So, the domain, in this case with respect to x, goes up to 4 at most, right? Now let's see where it starts from. I mean, from the left side. Let's see. If you stand at 0, the curve is here too. If you stand at -1, it's here too. It's also here. Here as well. If you stand here, it's also here. It's also here. And it's good too. Up to here, that's it, right? Because if you go further, the curve won't be there anymore, right? So what is the domain? I'll repeat. The domain is that interval of values that x can take, in very simple terms. Okay, so, from where? Where does it go? In this case, well, it goes from -1, -2, -3. Let's see again. -1, -2, -3, -4, -5. It goes from -6. I'll put it like this. From -6, considering -6. How far does it go? Up to 1, 2, 3, maximum 4. Well, what I just wrote is already the domain for this function that I'm making up here. Okay, so that's the domain. That interval of values that x can take. And what would the range be then? Because the problem also talks about the range of the function. Well, for the range, let's do something very similar. But we're not going to look up or down. We're going to look to the left and to the right. So that's what we're going to do. But with respect to the axis of the and now, imagine that you're on a staircase. For example, that staircase can go down, or it can also go up. Okay? So then the range will be, I stand, for example, here. Let's see, if I stand here and turn to the left or to the right, I run into the curve. I mean, I run into the function, right? Or not. Now, if I stand on the next one, for example, here, I'm going to stand here, I find the function. Yes, here, I do find it. And if I stand over here, here I am. I run into the function. Yes, I do find it. And if I stand at 0, yes, it's also here. Look. And if I stand at 1, yes, to the left and to the right, the curve is there. And if I stand, for example, here at 2, it's here, and it's here as well. And if I stand here, well, to the right it's not there anymore, but to the left it is. So the curve is still there. And if I stand over here, it's there too. So, well, not here anymore, right? Here, neither to the left nor to the right. So in this case, the range, as you can see, goes from, let's use another color. It goes from -1, -2. I'm going to start it from -2. And where does it go up to? Up to 1, 2, 3, 4, from -2 to 4. This right here is already the range of the function. Of this one I'm making up here. Okay, so when we are going to solve exercises of this type, remember, it's important that you refer to this exercise I just showed you. All right, so I'll erase this here and we'll continue. With this brief introduction to domain and range clear, let's go ahead and solve the exercise now. Look, right from the start, I want you to notice that in the function they've given me, we have a negative in the numerator and we also have a negative in the denominator. But we already know that a negative divided by a negative is a positive. So it's really not necessary for us to include those negatives. So I'm just going to leave it simply as 5 over the square root of x plus 2. Now I'm going to start asking you some questions. And it's important for you to think about whether what I'm going to say is possible or not. Let's see. I'm going to write down some values for x here. For example, x equals -4, x equals -3, x equals -1, x equals 0, and x equals 5. This is so we can see if we can plug any of these values in here, that is, in the position of x. Start thinking about it. Look, let me ask you, can I say that x equals -4 and plug it in here in the function? Is that possible? Let's see. If I plug in a -4, I get -4 plus 2, and -4 plus 2 equals -2. And no, square roots of negative numbers don't exist, so x can't be -4. So let's cross it out. That's not possible. Now can I put in a -3? Well, no, right? Because if I put in -3, I'd get -3 plus 2, and that's equal to -1. And the square root of -1 doesn't give me a real number, so it can't be -3 either. Careful. Now I'm going to skip all the way to 5 because I'm tired of the negatives. So let's go with the, could x be 5? Yes. Because I'd have 5 plus 2, which is 7, and the square root of 7 does give me a real number, and 5 over 3 gives me another number. So yes, it can be 5. And could x be 0? Let's see. 0 plus 2 equals 2. The square root of 2 is real, and 5 divided by something. If I get something like that, then x can be 0. And can x be -1? Well, yes, too. I'll write it down right away. Look, if I plug in -1, I would get -1 plus 2, which equals 1. And the square root of 1 is 1, and 5 divided by 1 equals 5. So when x is -1, the whole function is 5, right? So it can be that value, but there's a problem with -2. And that's exactly why I left it for last. Look, what happens if I put a -2 here? If I put a -2, the following will happen. Look, I'm even going to write it down because that -2 is so important. And it's no coincidence that in the range, in the domain, we have -2 repeated here because that number is really important. So I'm going to write that y equals 5 over the square root of what? Well, I'm going to plug in a -2, so I'd have -2 plus 2. If we do this operation, I end up with 5 over the square root of -2 plus 2, which is 0. This is like 5 divided by the square root of 0, if that's possible. The square root of -1 isn't possible, but the square root of 0 is, and it's 0. Now, what you can't do is divide by 0.5 divided by 0 is not possible. So x equals -2 can't be taken either, in this case. I'm going to mark that it was possible to substitute because of the square root, but I'm going to put a little cross to indicate that you can't divide. Let's see. The problem is that it could be -2. Well, the answer is that value. I mean, it can't take the value of -2. But if it's going to start from there, what do I mean? Look, I'm quickly going to draw a little number line here, and we're going to mark some of the numbers. Some of the numbers I've been talking about. For example, well, here's 0 for example. Here's 1. Here's 2. And I'm going to put -1 here. And over here is -2. Let's see. Well, I'm also going to let's go ahead and put -3. We had agreed that -3 wasn't possible, right? This one? And for -2, well, we're still undecided, okay? So, what I'm going to do in this case is draw a little line. I put a little circle to indicate this one. The values of x will start from -2, but they can't actually take that value. You'll see what I mean in a moment. Now I'm going to draw an arrow, but pointing to the right. Why am I drawing it to the right? Because we already saw that starting from -2, without actually being -2, it can take those values. I mean, it can be -105, and so on. So the domain will be that interval of values that goes from -2 without including -2 up to infinity. That means, for example, that I can put, let's say, 100 yes. I can put 100 for x, so it would be 100 plus 2, which would be 102. And then we would have 50 square root of 102. And that's possible, right? So, if we can take any value that's greater than minus 2 in front of the differentiator, when I say greater than minus 2, I mean here. Another one that we could put here in the minus column would be 0 normally. We put it here for x, because if I put it, I would get minus 1.9999 like this, plus 2, so I would get 0, 0, 0, 0, 0, and so on, right? So we would have the square root of that 0.0000. And finally, we would have 5 divided by that square root. So as you can see, when x is this value, we can plug it directly into the function. But when x is exactly equal to minus 2, we can't plug it in. Okay, so I can get as close as I want to minus 2, but without actually taking it. That's exactly the idea. That's why I'm saying it starts from minus 2, but goes up to infinity. All right. So how can I represent that x goes from minus 2 up to infinity? Well, it's very simple. I'm going to say that x has to be, well, it has to be greater than, well, that minus 2, right? Just by saying that, this is enough to say that it goes from minus 2 without touching it, and goes up to infinity. Well, this will be the domain. We're done. Right now, I'm taking a bit longer to explain this, because I imagine this is one of the topics that's most difficult for you. So the answer will be the one where x is greater than minus 2. Let's see, does the option have that? X greater than minus 2. Look, option B looks like it. But it says x greater than or equal to minus 2, and not just greater. It can't be. I can't plug in a minus 2 here, as we've already seen, right? So, not this one. Then it says here, option C has nothing to do with it. It says x is less than or equal to minus 2, so no. And this one says x is less than minus 2, no. Not that one either. I mean, not less. It has to be greater, right? Ready. With this, we would finish exercise number 48 because we've already found the domain. So we're already ruling out the others, right? But again, since you're here to learn, I'll continue with the solution to the exercise. Now what I'm going to do is find the range. Okay, and to find the range again, we're going to do something very similar to what I just did. Let me erase. Well, I think I'll erase this as well, so I can have a little more space. Look, actually, that's not true. I'm going to need it, so I'd better leave it, and I'll just erase this part over here. Maybe this too. All right, let's do the following. Now I want you to think, but on the y-axis, you're going to think about the following. Let's see. Imagine a very large value for x, a really, really large one. For example, 100 million, okay? 100 million, so I would have 100 million plus 2, right? That would be 100 million 2. Now, the square root of 100 million 2 would also be a really big number. I don't care to know exactly what it is. Okay, but it's a very large number. Now, what happens if I divide 5? I'm going to write it down. Well, yes, I'll have to erase this. Excuse me, let me erase that. But anyway, follow my idea. Okay, what happens? If I divide 5 by a very large number, then in this case I would have 5 here. I'm going to write 5 divided by large. Okay, think about that. You have a 5 and you divide it by an extremely large number. Think, for example, about a pizza and divide it among a very large number of people. What would each person get? If, for example, you had a pizza and you were going to divide it among 100 million people, what would you have left of the pizza? Well, a tiny little slice, right? You'd barely even see it. So, really, the more people there are, the piece of pizza you get tends to be 0, right? I mean, it tends to be very small. Therefore, let me put it this way. If I divide 5 by an extremely large number, this value tends to be 0. But keep in mind, it's never actually 0. So let me put it like this. Look, I'll write it just like this. Okay, 5, let me say it this way. It tends to be 0, okay, because it's not 0. I mean, again, if I have a pizza and I'm going to divide it among a very, very large number of people, no matter how big that number is, I'll always have a very small piece. Okay, let's say I already have a small piece like this. And then, oh, we doubled the people. So, we cut it in half each time. I mean, I'm never going to end up with 0 pizza. I'll always get a very small piece, always smaller. So, yes, it tends to be 0, but it's not 0. Why am I telling you this? Well, because with that, we really have the solution. When I divide by a number that's very large, that's when x is extremely large. The answer tends to be 0. I mean, it tries to be 0, but it's not 0. Okay, it necessarily has to be greater than 0, right? That's why we're saying here that the range is greater than 0. Why? Because the result for y necessarily has to be greater than 0. Now, how do I know it has to be greater than 0? I mean, we already saw that, right? That when I divide by a very large number, the answer tends to be 0. But what if it tends to be 0, for example, down here and not up here? I mean, do you get what I mean? I already know that when I use a very large number, it tends to be 0. But is it above or below? I mean, does the graph come from up here or down here? Well, actually, it comes from above. Why do I say it comes from above? Let me tell you. What happens now, on the other hand, if we divide by an extremely small number, well, not extremely small, but rather extremely close to -2. Because remember that from there, that's where the range started, right? So, for example, the little number I gave you a moment ago, let's suppose -1.9 again. 999999999. It left me with 18 in the end. What's going on? If I put this value here in x, well, inside here, I'll get, so let me change the color. I'll get that. And that's equal to 5 over the square root of what? Well, of -1.9999, and so on plus 2. What's that going to be? Well, it's going to be 0.000 and so on, right? And well, in the end, there's going to be a 1 somewhere, right? So here I would have 5 over this right here, which is going to be a very small number. So here I'm going to write 5 over small. And what happens if I divide 5 by an extremely small number? Well, the result tends to be large, so the result is going to be large. When I divide a number by a very small number, the result is huge. For example, think about something very simple. What happens if you divide, for example, 1 by a really tiny number, like 1/100th? If you divide 1 by 1/100th, you'll get 100, right? Do the division so you can see. So, look, the smaller the denominator is, here I'm using 0.01, the smaller the denominator gets. The result of 1 divided by that small number tends to be a really big number. Therefore, when I use a value that's really close, at least to 2, I get a really big number, okay? And when I used a number that was extremely large, what happened was I got a really small number. So, what does that mean then? Well, that the range, in this case, is greater than 0. Okay? Look, I know I said a lot of things here, and I know it might seem very complicated for some of you, but it is important that you are well aware that this is in the guide and that you could be asked about it. Right now, I took much longer to explain it, because I thought it was necessary to give you a little introduction so you could understand it a little better. But there really are a lot of things here that you definitely have to learn, okay? All right, let's move on. Exercise number 49 says the graph of the function y equals -x minus 1. It corresponds to a line where y has a space from left to right, and it crosses the y-axis at... Well, this one might seem really hard, but it's much simpler than the previous one. Look, I'm going to write here the function that was y equals -x minus 1. And now I'm going to say two things. For example, x is equal to 0, and I'm going to calculate y. And I'm also going to see what happens if y is equal to 0. Let me do that, okay? So, let's see. If x is equal to 0, what would I get? Well, we would have that y is equal to -0. I'll write it down if you want. -0. -1, so y has to be -0 minus 1, which is equal to -1. So how would the coordinate look here? Well, 0, I mean, 0, minus 1 is the coordinate. Let's see what happens next. And now what happens? If y is already equal to 0 in this function, we would have 0 equals minus x. Okay, move x to this side, and on the right side, we automatically have a minus 1. So the coordinate, when y is 0, is x equals minus 1. So we would have minus 1, 0, right? There it is. It's ready. Now we have these 2 points, which are actually the intersection points, right? Let's see. I'm going to plot them here, even though it might not look that nice. Let me just put the graph here. And I'm going to exaggerate a little bit here with the axes too, so it looks a bit nicer. Okay, so I'm going to say, for example, that there's a 1 up to here, and there's also a 1 over here done. So let's plot these 2 points. Or, well, place these 2 points on our Cartesian plane. 0. 1, where is 0? 1, it will be here, right? 0. 1 and the other one is minus 1. 0, minus 1, 0. All right, so let's draw the line that passes through those 2 points. I couldn't see it at first. There, that's better. There it is. Now it's ready. We already have the line that passes through those 2 points. Now let's read again. And with this, we can answer. It says, I already have the graph of the function. This one right here. Sorry, it's this one right here. It corresponds to a line that, in this case, in the options we have the words ascends and descends. In this case, the graph descends, right? I mean, it goes down. If we look at it from left to right, then here it descends from left to right, okay? And where does it intersect the y-axis? Remember, this is the x-axis and this is the y-axis, where it intersects the y-axis, here. And which one was that? Well, that was 0, 1, right? At 0, 1. So what's the solution? It's decreasing and 0. 1 decreasing, decreasing, and 0. 1 is this one, right? Decreasing and 0, 1. All right, there it is. We're done. That's it. Let's move on to exercise 50. There is a box with a lid with a rectangular base. Pay attention, with a lid. 4x long by 3x wide and a height of 10 centimeters. The expression that represents the area of the box as a function of x is, let's see. Let's draw the box first. So here we have a little box. Well, the box didn't turn out that well because it looks a little ugly there, but you can more or less understand it, right? There we have a box with a lid. It says, it's a box with a lid. All right, let's put the measurements, it says. It's 4x long, so here it's 4x by 3x wide. So over here, sorry, over here we'll put 3x, which is what it has. So, to the front or over here? And in height, it's 10 centimeters, so here it's just a constant amount, 10 centimeters. Okay, done. It's asking me for the expression that represents the area of the box as a function of x. Let's see. What we have to do then is calculate the area of each of the lids. Okay, and simply add them up. But are there really repeated lids? Or, well, sides. Are there repeated sides? What do I mean? For example, think about this side face. This face over here, well, it has the same area as the face we have over here, right? The area of one of them and multiply it by 2. Now it's also true that the area down here, well, the area of the bottom lid is the same as the area of the top lid, right? And also, although you know it's a little stranger, but the area of this one here in front is also the same as the area back here, right? Right? Let's do it. Well, look at me. It's very simple. Let's say that the area as a function of x is going to be equal to 2. Times what? Well, let's start, for example, with bueno in the same order as them, and let's go with these lateral faces. In this case, since it's a rectangle, let's look at its measurements. Its measurement is 3x for the base times the height. What's the height of this face I have here? Well, it's 10, right? So I would have 3x times 10 for this face. But we said there were 2. That's why I put a 2 here. So I have 2 times the base, which is 3x, and times the height, which is 10 plus another 2 again. Now let's do the top and the bottom one. Let me change the color for the bottom one. Sorry, it's this one right here. So would it be this? Oh, sorry. This, and with this one, right? All right, we already have this one, and if we multiply it by 2, it will give us the area of the bottom one and also the area of the top one at the same time. So let's go. Let's check their measurements. So would it be then? The base measures 4x, it's a rectangle too, right? And the height of that rectangle is 3x. Therefore, I would have 2 times 4x times 3x. And to that, we're going to add, I'll write it down here below. We're going to add the area of the face that's in front. There are 2 of those, one like this and one back here. So, it would be 2 times. Let me point out the 2 faces, or, well, just the front one, which would be this one right here. Look, I'm referring to this one right here, the one marked in red, and obviously the one on the other side, right? Now, what would its measurements be? Well, in this case, it has a base of 4x and a height of 10, right? So let's write that down. Then we have 2 times 4, x times 10. All right. Now all that's left is to do the operations and simplify. All right. Let's start by simplifying. 2 times 3x is 6x times 10 is 60x, so we write 60x plus. 2 times 4x is 8x, and 8x times 3x. That's 24x squared. So let's write 24x squared. And finally, plus 2 times 4x is 8x, and 8x times 10. That's 80x, so it would be plus 80x. We simplify like terms and arrange them. We start by writing the one with x squared, which is the 24. And here we have 60x plus 80x. 60 plus 80. That's equal to 140, what x? All right, this is the solution to the exercise. 24x squared plus 140x. We have that. 24x squared plus 140x. And that would be option B. Right? And that's it. We're done. Much easier, right? All right, let's move on. Let's go to exercise number 51, which says, determine the value of the sine of b in the triangle shown. Look, the sine is defined. I'm going to write it here. The sine of an angle, theta, any angle, is defined as the quotient. Between the opposite leg, I'm going to write it like this. Opposite leg, and the hypotenuse, this is the sine. Opposite leg over hypotenuse. In this case, they're asking me for the sine of b. That is, the sine of this angle I have here. So let's write that the sine of b has to be equal. Well, according to the formula, the opposite leg for this angle is 2. Right? The adjacent leg is 1, correct? And the hypotenuse, well, it's this one, which is the largest. So let's write the opposite leg, which we said is 2. And this is going to be divided by the hypotenuse, which is the square root of 5. And that's all we have to do. So let's leave it like that. That's it. What would the solution be? 2 over the square root of 5. Where is that here, right? Part A, done. That's it. That's all. Let's write it down. Exercise 52, which says, a pole casts a shadow, 1.5 meters long at the moment when the angle of elevation of the sun is 60 degrees. What is the height of the pole? All right, let's draw the pole. I'll put it over here. There's the pole. And now it's telling you that the pole, casts a shadow of 1.5 meters. Well, let's suppose that over here. Let me see. I'll leave it in color. Over here, the shadow of the pole is cast. But it turned out really ugly. Let's suppose that's it, okay? And it's telling you that shadow is 1.5 meters long. What else? Then it says the angle of elevation of the sun is 60 degrees. Let's see. With this, we could think the sun is over here. Okay, like this. And then it says it's at 60 degrees. Therefore, I could set a reference point after the... And it would have to go through here, by the post, by the top part of the post. It would have to happen. So if the angle of elevation of the sun is 60 degrees, then this angle I'm marking here should measure 60 degrees. Right? Ready? As you can see, this is a right triangle. There's a right angle here, right? So can I use the Pythagorean theorem for that triangle? Or can I also use trigonometric ratios? In this case, as you can see from the shadow of the shadow, an angle theta is defined as the quotient between the opposite side, I'll leave it like that, over the adjacent side. Well, the trigonometric ratio is opposite side over adjacent side. So let's see. Let's substitute in this case. So I have that the tangent of theta, which in this case, let's say yes. Shadow of the shadow of the shadow. The shadow of the shadow. Of the shadow of the multiplying. So I'm going to have 1.5 times who? Well, times the tangent of 60. But they're already telling me here that the tangent of 60 is 1.73. So I'm going to put 1.73 right away. This is going to be the value of x. That's it. That's all we have to do. So now we just have to calculate. I'm going to do the multiplication quickly. So we put 1.73, just 1.73 times 1.5. Let's do this multiplication quickly. 5 times 2 is 10. I write down the 0, carry the 1. 5 times 3 is 5, plus the 1 I carried is 6. 5 times 7 is 35, plus the 1 I carried is 36. 7 times 3 is 7 times 1 is 7 and the 3 I carried. Makes 10. Now let's multiply by 1 times. 2 is 2 1 times. 3 is 3 1 times. 7 is 7 and 1 times 1 is 1. Let's add them up. We bring down the 6, plus 2 is 8 plus 3 is 11 plus 7 is 18. Carry the 1 plus 1 is 2 in total. We have 3 and 1 more makes 4 decimals. So I move over to 1.234. Here. So the decimal point will go here. And now we have the result of the operation. 1.5 times 1.732 gives me 2.598. Right? So what's the solution? 2.59 more or less. 2.6, that's it, right? 2.59 meters here. It actually would have been better to round up to 2.6, not 0.6. But anyway, that's fine. That's the solution. So, from the exercise, let's go to exercise 53. Which of the following exponential functions has a range from 1 to infinity? Look, I recommend that you don't just stick with this guide. I mean, not just with guide 4, but also check out the other guides. I'm solving each of the 4 guides in detail, so that you all can study from all of them. It's important, because in some of them, I clarify a bit more about some of the exercises. And the truth is that the topics are basically the same. The only thing that changes is the level of difficulty. If you are good, are you going to study in Area 4? They really won't ask you questions as complicated as those in Area 3 and those in Area 3. At the same time, they won't ask you questions as complicated as those in Area 2. And it's the same, okay? So, the ones who get the most complex math questions are those in Area 1. But really, the topics are basically the same. I mean, everyone will be asked about functions. It's just that the level of difficulty will decrease as the area number increases, okay? So if you say today, like, that topic wasn't very clear to me, so something you could do is simply review the previous videos, because these are topics that were already covered in the other guides as well. All right, now I'm going to solve this exercise. They're asking me for the function that has a range that goes from 1, not including it, up to infinity. And as you can see, we have some exponential functions here. Let's take a quick look. I'm telling you, This is the answer. It's this option, because I justified it. Look, when we have the graph of a function, for example, like a to the x, let's note the following. Pay attention. The function f of x equals e to the x. Draw a curve, and this curve goes up, passes through, 0, 1, and then continues like this. This one here is the graph of the function f of x equals e to the x, okay? The range of this function is from 0. I put 0 up to infinity. Why? Because those are the values it can take. There. Look, it starts from 0 without touching 0, and it goes up, 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 and this will always keep going up. Okay, up to infinity. Would that be for the function f of x equals x? Now, if the exponent changes, it's really still the same range. The only thing that changes is just the way the graph grows. Okay, if the exponent changes, but really the range will be the same. When the range does change, that's when it will change. If we have numbers out here, whether adding or subtracting. So as you can see, this one here is not the solution because it basically has the same range as this one over here. I mean, it says from 1 to infinity, not 0 to infinity. This one isn't it either, since it also has the same range, from 0 to infinity. That's why I said moving the exponent doesn't really change the range. Where will it actually change? If we have here or here a number that is either being added or subtracted, if the number is being added, what it means is that this graph I'm drawing here, we're going to move it up. In this case, 1 unit. And if this number is being subtracted, then it means we're going to move the graph down by 1 unit. So in this case, for example, if I wanted to plot the graph of the function f of x equals e to the x plus 1, I mean, the plus is outside, well, down here. So it would look like this. I would draw the same green curve, the same one, only now it's going to go up a little bit, and it would look something like this, right? Well, it looks a little messy, but that's the point. What I'm doing is taking this green graph. Let me do it again. I'm repeating this green graph, only now it's shifted up by 1 unit. That's what I'm doing. This one I have here in orange, well, it's f of x, which is equal to e to the x plus 1. And it's the same. Remember, if it were f of x equals e to the x minus 1, then it would be the same graph, but it would start from -1 and go up. Are you following me on that? All right. So now, which one is it? Which graph has this range? Sorry, which function has this range? Well, as you can see, it's this one, right? Because it's the one that's making it go up by 1 unit. Is that okay? I want to clarify something. What I'm doing here are sketches of these two graphs. It doesn't mean they're exactly like this. Okay? Because they're not coming out that nicely. Anyway, do you want to see exactly what the graph of this function looks like? Go to GeoGebra, enter it, and you'll see that it looks a lot like what I just showed you. Okay, so let's continue. Let's move on to number 54, which is the line that looks like this. In total, the function y equals the logarithm base 4 of x minus 2. Let's see again. To make this much clearer, let me explain a few things to you. Before we can quickly find the asymptotes, while I draw the Cartesian plane here, let me remind you that an asymptote is a line that the function cannot take. That would be the asymptote in very simple terms once again. I'm going to show you the graph of a very common function that will serve as a basis for solving the exercise. Here we have a curve that comes very close to the axis at 10, but without touching it, it goes up little by little, then passes up here and starts to curve. Okay, this curve I just drew corresponds to the function f of x, which is equal to the natural logarithm of x. As you can see, what I'm doing here is getting very close to the axis at 10, but without touching it. And then it goes up, 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 and starts to curve. Then, okay, well, it was always a curve really, but then it starts, how can I say it, to flatten out a little bit over here, and then it just keeps going. In this case, for example, the asymptote, as I just told you, is a number that can't be touched. Let's see here. It came out ugly because it didn't understand it. What did I just write? Let's see. Let me write it correctly, without any mistakes. In this case, the asymptote is that x equals 0 for this function, because I say that x equals 0, because I just told you that this curve goes down, 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 but it doesn't touch the x-axis. So since it doesn't touch the x-axis, that means x can't be 0. It starts from there, but it can't be 0. So here we say that there's an asymptote. There's an asymptote right on the x-axis. Okay, well, this works. This works. Sorry, no, that's all. For the function f of x equal to the natural logarithm of x, it would also work, for example, for the logarithm base 10 of x. That is, it would be a very similar graph. And it would also work if we have a different base. For example, logarithm base 4 of x, which is something like this. But now here we have logarithm base 4 of x minus 2. When inside the parentheses we have a number, whether it is being added, being subtracted. Sorry, I meant we are going to shift the graph of the function by these units that are indicated here, but in the opposite direction of what it says here. That is, if you have a negative, it means that the entire graph is shifted 2 units to the right when it's negative. But if it's positive, it means the graph of the function is shifted 2 units to the left. So if it's subtracting, it goes to the right. If it's adding, it goes to the left. That's why I say it does the opposite. In this case then, as you can see, since I'm going to shift this graph 2 units where? To the right. That gently Schwartz, the one who arrives in November so that she can start playing. And what would the function's graph look like? Well, now I'm going to do it in color. This one is going to stick here, and then to cross over and then come over here, okay? So would it be something like this? Therefore, we would already have the graph of the function f of x equals the logarithm base 4 of x, of whom, well, of x minus 2. Because again, we were shifting 2 units to the right. In this case then, what would the asymptote be? Think about it. It's simple, right? It would be x equals what? 2, right? Because I'm shifting 2 to the right. That's it. So, what's the correct answer? Is it x equals 2? This one right here? So we circle option C. Done. We're finished. All right. Let's continue. Let's move on to exercise 55. The slope of the line that passes through points H and K is equal to A, and they give us 4 possible answer choices. We're going to calculate the slope using the following formula. We're going to put 2 minus y1, and we're going to divide this by 2 minus x1. Who is 2? Well, it's the y from point 2. Who is 1? Well, it's the y from point 1. So, and well, who is x2? It's the x from point 2. And who is 1? It's the x from point 1. So if I say, this is point 1 and this is point 2, then this would be x1. This would be y1. All right, we substitute, that's it, and we simplify, and that's it. And it's worth mentioning that I could also say it the other way around, okay? That this is point 1 and this is point 2. It doesn't matter. All right, so I get this. And Yishi 2, which in this case would be minus 1. We put it in the formula. Minus y1, which is 5, over x2, which is 6. Minus x1, which is minus 8. Here I'm going to open a parenthesis to separate the 2 negative signs. All right, let's do the math. Minus 1 minus 5 is minus 6. And in the denominator, we have 6 minus minus 8. Minus times minus is plus. So I would have 6 plus 8, which is 14. We simplify this fraction. Minus divided. By plus is minus. Half of 6 is 3, and half of 14 is 7. The result then is minus 3/7, which is right here, right? Minus 3/7. Done. We box the answer. Minus 3/7. That's it. Let's continue. Exercise 56. Which of the following slopes corresponds to a line perpendicular to A and is equal to 3 minus x? Let's see. First, I'm going to rewrite this equation, and I'm going to put it in a specific form. I'm going to write y equals. I start by writing the minus x, which I'm going to write as minus 1x. It's still minus x, right? Plus 3. Okay. I just wrote it like this so that it looks a lot like this form, y equals mx. So what am I saying with that? Well, I'm saying that the m in this case is equal to what? Well, to minus 1, right? M equals minus 1 and b equals 3. So the slope is minus 1 for what? For that perpendicular line, the line that's here, but I don't want to know the slope of this line, but rather the slope of the line that's perpendicular to it. So we need to know something called the perpendicularity criterion. The perpendicularity criterion tells you that slope 1 times slope 2 has to equal minus 1. In other words, if you multiply the slopes of two lines and the result is minus 1, it means the two lines are perpendicular. That is, they form 90-degree angles. So, with that information, you already have what you need to solve it. Let's say it's slope 2 that I don't know, but I already have slope 1, which is the slope of this line. So I would have slope 1, which is minus 1 times slope 2, which is the one I don't know. That's equal to minus 1. And well, from here we solve for slope 2. So I get minus 1 divided by minus 1, and that's 1. So the slope, line 2, is equal to 1. We select option B. Done. We're finished. What is the general equation of the circle with center at 0, 0? And that passes through the point 2, 0. Let's see. Once again, we're going to have to make a Cartesian plane. Honestly, I've been making quite a few Cartesian planes, haven't I? I think next time I'll have a model Cartesian plane ready, so I don't have to draw it every time. All right, so here we have the Cartesian plane, and they're telling me that the center is at 0, and also that it passes through the point 2, 0, 1, 2, 0. So it passes through here. Let's see. We have a circle that meets those characteristics. Let me see. It looks nice, huh? There it is. Look. Done. Well, that's where it was really drawn. I said circle. It's a circumference. We have a circumference that meets those characteristics. Don't pay attention to what's drawn here in the center. Remember that the circumference is only the outline, okay? Or this part that I'm marking here in red, more or less. But if I let go, it's going to get drawn. But anyway, remember, it's only the outline, okay? Not the center part. All right. The equation of the circumference in its standard form looks like this when the center is at the origin. Let's write x squared plus y squared equals r squared. That's in the standard form. If we want it in the general form, let's write x squared plus y squared. And we move this r squared over here to the left side. This is the standard form, and this is the general form. Now, what do I have to do? Well, just substitute, because honestly, they're giving me everything. I just had to remember that this is the form. All right, so I end up with x squared plus y squared minus. The radius squared, what's the value of the radius? Well, it's 2, right? So I would have minus 2 squared, which is 4. It has to be 0. That's it. That's the one right here. So, that's the equation of the circle with its center at the origin, which has a radius of 2, right? So, which one? Do we pick option B? Right? Okay, that's it. We're done. Let's move on to number 58. The equation of the circle with center at -1, 1 and radius equal to 3 is, and they give us 4 options. Three squared. And we ask, well, let's see. Let's fill in. Is it correct? Yes. Do we bless? Is it -1 the blue? To deny a million of ice cream, can you count it out? How much is it worth? Squares, all right. How much is there at any point? Let's put it like this. We write x minus h, raise it to the power of 2, plus y minus k, raise it to the power of 2, and we set it equal to r squared. This, I insist, is the equation of the circle with a point. Sorry, with a center anywhere on the plane. Okay, in this case, we have a point that's at -1. 1. Sorry, -1, 1. Here, right? Here will be the center. And we also know that the radius is 3, so it would be 1, 2, 3. So it has to go through here up to here, right? Let's see if it turns out nice this time. All right, I just put this little formula here for you, and I'm sure these parts stand out to you, right? I mean, it's h and k, very simple. The center has coordinates h, k. So in this case, I want you to see that they're already telling us the value of h and the value of k. Why? Well, because it's saying that the center is at -1, and remember that the center has coordinates hk. So I already know the value of h and the value of k, so I can already say that h is who? Well, -1 and k is who? Well, 1, right? All right. Now, how much is r worth? We had agreed that it's 3, all right. And from here, we get that the radius squared is equal to 3 squared, which is 9. Therefore, we already have everything. We just need to substitute here. How does it look? I'll write it down here below. So we have x minus h. But h is -1, so it would be x minus -1, which gives me x plus 1, right? We raise it to the power of 2. Then it's plus parentheses and minus k. And minus k. But k is 1 squared, and this is equal to the radius squared. But the radius squared is equal to 9. There you go. We already have the equation of our circle that meets those characteristics. Okay, well, I'll leave it there. What is x plus 1 squared plus y minus 1 squared equal to 9? Is this true? Let's see. Anyway, I'll check the others so I don't make a mistake. If that's it, that's the solution. Let's go. With number 59, calculate the vertex of the parabola. Y minus 3 squared equals 12x minus 24. Let's see. The first thing I'm going to do is put the equation, well, one of the two equations of the parabola. This is y minus k squared equals 4p times x minus h. I say it's one of the two, because there's one for vertical and one for horizontal. The other one would be x minus h squared equals 4p times y minus k. But right now, does it really matter which one is for vertical and which one is for horizontal? Because what really matters is to observe what the coordinates of the vertex are. And look, the vertex has coordinates h, k. Now we would have to look at this and compare it with this, so we can know which one is h and which one is k, and with that, we find the vertex, right? But if you notice, while the left side looks similar, the right side doesn't look as much alike. Why? Because of what's on the right side. Over here we have a 4p that's already factored. So what I'm going to do next is write the left side again just as it is. That is, y minus 3 squared, and on the right side, we're going to factor by common factor. What's the common factor? For 12x and 24. It's 12, right? So I write 12. I open parentheses, and now I ask, by what do I multiply? 12 to get 12x? By x. Minus, by what do I multiply 12 to get 24 by 2? All right. As you can see, now we have the same form. Let's see who's who. This minus k will be, that minus k will be minus 3. So, since minus k is minus 3, what does that mean? That k equals 3. Right. Now this 4p is the 12, but I don't care about that. But this minus h, which I do care about, is equal to minus 2. If minus h is minus 2. What does that mean? That h equals 2h equals 2. Therefore, now we have the vertex. The vertex had coordinates h, k. So in this case, 2, 3. All right, so the solution is that the vertex has coordinates 2, 3, which will be option A. All right, let's move on to exercise 60. The ellipse is the geometric locus of the points on the plane. So, well, they give us 4 possible answer choices. Let me explain briefly. We have any ellipse. Let's suppose this one. Let me make it a little nicer. Let's suppose something like this. Now we have an ellipse there. Okay, good. Now I'm going to put 2 points in here, which will be this one, for example, and this one right here. I'm going to call this one F, which is actually called a focus, and this one I'll call F, which is another focus in the ellipse. The following has to happen. It has to be that if we place a point, for example here, and another point, for example here, and another point, for example here, the following will always happen. Look, if you draw a line from the focus to the point and measure it, and then add another line that goes from the point to the other focus, this sum, that is, the length of this plus the length of this, has to be the same as the sum of the distances to this other point. That is, if I draw, from here to here and measure it, and then draw from here to here and measure it. Well, the sum, it got colored in. I don't want it to get colored in. I'll put it like this so it doesn't get colored in. If it did get colored in, let's see. It's just that I don't want it to get colored in, because I don't want you to think about the region. I'm going to put it here a little farther apart. Okay, there it is. Look, so it should be that the measurement of this plus this has to be the same as the measurement of this plus this. That is, the whole blue line has to measure the same as the whole green line, and also the same with the purple dot. So if I measure from here to here, this plus this right here has to be the same. Well, up to here, up to the focus. It has to be the same as what the blue line measured and what the green line measured. That has to happen, okay? So, remember that in the ellipse. Let's see if any of these talk about that. Come on, let's check. The thing is that the difference, it's not a sum of distances. This is not a sum. Here it is. The thing is that the sum of their distances to two fixed points called foci is a variable value. It's not, no. It keeps changing. Otherwise, well, it would be a mess. Right? Is there? It's constant. So that's not it either. The thing is that the sum of their distances, to two fixed points called foci is a constant value. That's right. That's exactly the definition of an ellipse. So that's why I wanted to show it to you here again. Does it talk about difference? No, that's not it. I don't mean the difference between these measurements. It's not the sum of the two distances from the point to each of the foci. It has to be constant. Okay then? Is that why? The correct answer, in fact, is option C. Let's go to number 61. Find the standard equation of the hyperbola with center at 3, 7, and focal axis parallel to the axis. And since it's talking about the focal axis being parallel to the axis, that means the hyperbola is vertical. Okay, because the focal axis, which is the line that passes through the foci, is parallel to the axis. And therefore, it's a hyperbola that is vertical. So I'm also going to give you the equation of the hyperbola when its center is not at the origin and it's vertical. Let's write it like this. We write y minus k squared. This is going to be divided by a squared. Then here we put a minus sign, and here we write x minus h squared, and this is going to be divided by b squared. And this has to be equal to 1. This is the vertical equation of the hyperbola when its center is not at the origin. In this case, the center has coordinates h, k. So as you can see, we already have everything. Why is that? Because they're already telling us what the center is. They're telling me it's at 3, 7, so let me write it down. 3, 7. Okay, so that means that h is 3 and k is 7. Now we would just substitute directly here and here, right? Notice that in this case, the options aren't giving me the values of a and b. Because really, for area 4, they're not asking you to find so many things. I mean, they do want you to study the hyperbola, but they don't want you to find everything. For those in area 1 and area 2, if you check the guides that I already uploaded, well, I haven't done the one for area 1 yet, but I already finished it, so you'll see it when I upload it. I already have the one for area 2. You'll notice that in that one, they do ask you for the values of a and b, but in this case, they don't. So here, we just need to focus on the coordinates of the center, and that's all we have to do. That makes it much easier. So I end up with y minus k, but k is 7 squared over something that's an a squared in this case. And that's equal to x, minus x minus h, which is 3 squared over b squared equals 1. That's how it should look. Where is that? It's a, right? Y minus 7 squared a squared minus x minus 3, yes, it's this one. So, would this be the solution then? All right, we're done. And let's move on to the last exercise, which says, what type of conic does the equation belong to? 3x squared minus 3y squared plus 6x minus 3y minus 5 equals 0. Actually, this is a question that, even though it's not theoretical, we do need some theoretical aspects to be able to solve it. And I'll tell you what I mean. Look. In the circle, for example, it's true that we need to have x squared and y squared. But in the circle, they are going to be added together. They necessarily have to be added. So it can't be a circle, because I want you to see that the coefficient of y squared is negative, so it's not a circle. Let's see, in the ellipse, what happens in the ellipse? Well, the same thing. It's also going to have x squared, and it's also going to have y squared, but in these cases, they also necessarily have to be positive. Okay. I mean, there can be numbers here. Sure, there can be numbers, but the thing is, they have to be positive. So this here can't be it either. What happens in the case of the hyperbola? Well, in the case of the hyperbola, they must have opposite signs, meaning one can be positive and the other negative. Therefore, the correct answer is hyperbola. That's it. This would be the solution. Well, let me put it in green, so we keep the same idea. There it is. So, the correct answer would have to be hyperbola. And well, finally, in the parabola, you either have x squared or y squared. Meaning, you can't have both x squared and y squared in the same equation. Therefore, it's not the parabola either. So in this case, the correct answer is the hyperbola. And well, with this, we're finishing this video. I hope the content was helpful to you, and, above all, that you liked it. If you did, please, I'm going to ask you that, if you've stayed until now, and if this content is helping you, it doesn't cost you anything. Please subscribe. And I'm also going to ask you for a favor right now. Recommend this video to someone you think it could help. Really, it's important that this kind of information reaches more people every day. Saying goodbye to you all, Jesus Grajera Rosas, Mathematics with Grajera. See you next time. Bye.